Hello, and thank you for joining us for this calfordseaden Sustainability CPD seminar. This video is a recording of a live session which was held in May 2020, and it covers the changes to the SAP 10 methodology and Part L consultation. The team members presenting the seminar are Dr Terry Keech, our Head of M&E Services, and Emily Mansfield, who is one of our sustainability consultants. For those who don't already know us, calfordseaden is a multidisciplinary construction and property consultancy with a trading history of over 70 years. All services are provided in-house by directly employed teams, and we operate from 6 offices located in London, Birmingham, Cambridge, Essex, Hampshire and Kent. We hope you enjoy watching, and please get in touch using the details at the end of the video if you have any questions or would like to register interest in future CPD sessions.
Presentation today then, we're going to give you a general overview of the key changes to the SAP methodology, which is affected by the building regulations and the change to Part L of the building regulations. We're going to show you the impact on the new carbon dioxide emission factors and different renewable technologies. We're also going to show you the impacts on primary energy. And the reason why we're concentrating on primary energy is that is going to be a main criteria of compliance with the building regulations, especially where we are using electrical energy, because the reductions in CO2, as you'll see during the presentation today, is really putting electricity at the forefront of that energy drive for new dwellings. We'll go a little bit through the main areas of Part L consultation. We'll give you some updates on the draft GLA London plan and where that's going, and another document has been released this week, so giving some more information on the London plan. We'll also give you a little bit of an idea on typical energy costs so that you can see how the changes in the building regulations, what that really means for the end user, because we're very, very keen at calfordseaden in not only achieving a low carbon development or a zero carbon development, but it has to be affordable for residents at the end of the day. And where we are looking at electricity as being one of those predominant elements, affordability is really, really key to us. So we will concentrate on that affordability. I'm then going to go on and give you a little bit of an outline on some of the heat pump solutions that are out there at the moment and will be possibly coming up from consultants and contractors and developers that you're dealing with. We'll do some recommendations and then we'll have a question session. So without any further ado, I'm going to hand over to Emily for the first part of the presentation. Emily, thank you.
Thank you very much, Terry. So we're going to start looking at the general changes to the SAP methodology. So the new Part L consultation was released in October last year, and with that also updated SAP methodology, version SAP 10.1. The current methodology is SAP 2012, which we use to assess against Part L 1A 2013 of the building regulations. SAP 10 was released in July last year, July 2018, sorry, so that developers, designers and consultants could see how the methodology would impact their designs. And that's the methodology that the GLA are currently applying to their new schemes. So what are the general changes to the SAP methodology? So the background calculation has been updated. This usually happens between the methodologies, just to make sure that the energy consumption is calculated as accurately as possible. For example, the heating pattern has been updated in SAP 10.1 to reflect the same heating pattern at the weekend as during the weekdays, because on research they found that people generally do keep their heating pattern the same throughout the week, whereas under the current methodology there's a completely different heating pattern for the weekend. The hot water now includes flow rates for showers and baths and the use of electric showers. So currently under the SAP 2012 methodology, we just put in whether we have a hot water cylinder or a heat interface unit and what kind of losses we get for them. So it doesn't really take into account what the flow rates are from our appliances. So under the new methodology, we can actually put them in, and it allows for the hot water consumption to be calculated more accurately. For showers, the minimum flow rate allowed in the SAP methodology is 8 litres per minute. So if you go lower than that to achieve your Part G compliance, you just won't see the benefit in the SAP calculation. But you may need to go lower to get your Part G compliance. Same with electric showers. The minimum output is 9 kilowatts. So again, if you find a shower lower than that for electric showers, you just won't see the benefit in the SAP calculations. But in reality, it would be a benefit. Lighting calculations have also been updated, so you can put in the individual efficiency of each light fitting. Whereas at the moment, we just say 100% low energy or 75% low energy. So again, it's just so the lighting energy can be calculated more accurately. The sum over heating criteria now takes into account air quality and noise pollution issues. So at the moment, if you have a flat on a mid-floor with no security issues, you can just say your windows are fully open all the time. So most of the time, you'll see that most dwellings comply with criterion 3 of Part L using this current methodology. Under the new methodology, we have to consider air quality and noise pollution issues. So we won't be able to say that the windows are open all the time if you're near a main road, a train station, or an airport, due to the air quality and noise pollution. So we may see more developments failing this criteria. Default efficiencies and ventilation rates have been updated to reflect the current market. So this just to make sure that we use the best products possible within our SAP calculations. And the thermal mass parameter has to be calculated. So at the moment we use a simple TMP of low for timber frames, medium for light concrete frames, and high for dense concrete frames. But this is more work for the SAP assessor rather than for the design team. So key changes. So these changes have the biggest impact on the SAP calculations. So the thermal bridging Y value default has increased from 0.15 watts per meter square Kelvin to 0.2. So at the moment, if we use 0.15 as the default, we will find that we have to make improvements elsewhere to the building fabric specification to achieve compliance. So applying the 0.2 will be quite difficult. At the moment, we can apply accredited construction details for our side values if we calculate the thermal bridging, but the ACDs are going to be scrapped. The government is thinking about bringing in another library with some standard details that we could apply to our SAP calculations, but it's likely that we'll need to carry out bespoke side value calculations. If you have a detail that you use on the development, so a cold bridging detail for where your external wall meets your ground floor, or your external wall meets your roof or an intermediate floor or your corners, then you can apply that detail. Once it's been calculated, you can apply that across the development. So you don't have to get each property calculated. So you can just use one detail that you apply across the development. And if you carry that detail across to another development, again, you can still use that same detail. So you won't have to get a new set of side values calculated, as long as the details are very similar. Solar PV array now recognises the use of battery storage and diverter. So a diverter uses electricity generated by the PV to heat your hot water cylinder instead of using electricity for your immersion. And this is basically encouraging us to use the electricity generated within our properties rather than exporting back to the grid. Due to the feed-in tariff closure earlier last year, this makes it more beneficial to the end user. Due heat and distribution pipework losses factor has increased from 1.05 to 2. That has a huge impact, and it's likely that you will fail the SAP calculation if you use a default factor of 2. If you use the CPS code of practice for district heating networks, then you can use a default of 1.5. But again, this is still high. And again, this is encouraging us to insulate to reduce heat losses. So we recommend that you calculate your distribution loss factors. The fuel tariffs, CO2 emissions, and primary energy factors have also been updated, which we'll look at now. Primary energy has been included because the proposed new Part L consultation indicates that under criterion 1, primary energy will also be a main performance metric. So it will be CO2 emissions and primary energy, whereas at the moment we look at CO2 and the fabric energy efficiency. Primary energy is basically all the energy used to produce your fuel and deliver it to your house. So for electricity, it's the mains gas, the coal, the renewable technologies, all the energy required to produce that electricity and deliver it to your house. Here are the updated fuel tariffs for SAP 2012, which is current methodology, and SAP 10.1, which was released with the consultation last year. As we can see for mains gas, there has been a slight increase in the cost for mains gas from 3.48 pence per kilowatt hour to 3.93 pence per kilowatt hour. For electricity, we can see that that has increased quite significantly from 13.19 pence per kilowatt hour to 17.56 pence per kilowatt hour. And it's worth noting how much different that is compared to mains gas. So it's almost 4 times higher than mains gas, the cost of mains gas. The electricity export has also reduced from 13.19 pence per kilowatt hour to 5.3 pence per kilowatt hour. And this is because of the closure of the feed-in tariff. There is a smart export guarantee, but electric suppliers can set their own price, which is why the SAP has taken a low rate of 5.3 pence per kilowatt hour.
Emily, could I just come in there?
Yep, yeah, of course. Yeah.
Just an interesting one for what we'll be looking at later on in the slides. The key point to note, as Emily's brought up, that electricity being 4 times more expensive than the gas, when we are then considering technologies such as heat pumps, the COP, the coefficient of performance, every 1 kilowatt of energy generated to how many kilowatts of heat being able to be produced. So therefore a COP of 1 to 2 is 1 kilowatt of energy for 2 kilowatts worth of heat. The COP of our heat pumps will need to be operating somewhere in the region of a COP of 1 to 4 to be able to get our tariff prices to residents similar to that which we're charging for gas at the moment. So just a highlighted point to show one of those implications on reductions in CO2 but increases in energy costs. Thanks, Emily.
Thank you, Terry. So here are the updated CO2 emissions. Again, we've got the current SAP methodology, SAP 2012. Then we've got what the GLA are using on the current schemes, which is the SAP 10 methodology released in July 2018. And then we have the most current update, which is SAP 10.1. So for mains gas, we can see that there's been a slight decrease in CO2 emissions per kilowatt hour from 0.216 kilograms of CO2 per kilowatt hour to 0.21. So it's just a 3% decrease there, reduction. Electricity, however, we can see that what the GLA are using has a 55% reduction over the current SAP methodology. So we're going from 0.519 kilograms of CO2 per kilowatt hour to 0.233. Now, under the SAP 10.1 methodology, we can see that that CO2 emission factor for electricity decreases even further. There's a 74% reduction over current methodology at 0.136. And it's worth noting that that is actually lower than mains gas, which is why we can see how we're being pushed down electric heating routes rather than mains gas. It's also worth noting that electricity generating technologies such as solar PV, you'll need more to save the same amount of CO2 as you do under current methodology. If you see my mouse there. So at the moment with PV, we're saving this much CO2. But under the new methodology, SAP 10.1, we're only saving this much CO2, but using the same amount of panels. So you'll need more panels in order to achieve the same CO2 emission saving as we do under the current methodology. So just to demonstrate that, we carried out an exercise in SAP Calculations using different heating systems and technologies. So on the left-hand side, we can see that we've got a gas boilers community heating system. And then we've got the current SAP CO2 emission factors, the GLA SAP CO2 emission factors, and then the SAP 10.1. And you can see that naturally, using the same specification, we get a 17% reduction in CO2 using GLA factors and a 22% reduction using the SAP 10.1 factors. Even though mains gas has the same CO2 emission factor for SAP 10 and SAP 10.1, because we got that reduction in electricity, we're saving even more CO2 for our lighting and pumps and fans, which is why we have a slight better reduction there. However, for solar PV, as I was just saying, you need more PV in order to save the same amount of CO2 as we do under the current methodology. And that's reflected here, where the CO2 emissions are actually higher under the SAP 10 and SAP 10.1 methodology when using the same amount of PV array, as in the SAP 2012 calculation. And that's the same with combined heat and power, CHP engines. Here we can see that we're not getting as great a saving as we would currently under the SAP methodology. And this is why we're moving away from CHPs in London schemes. When you apply electric heating systems, you can see that you're getting your 55 and 74% reduction in CO2. However, it is worth noting, especially with direct electric heating, that your EPC certificate can have a very poor rating because this is based on your running costs. And as we saw in the previous slide, the cost for electricity is so much higher than mains gas. So in order to get a better EPC rating, we'll have to make further improvements, such as to the building fabric specification or implementing renewable technologies and on-site electric storage, such as battery or diverters.
Emily, could I just drop in here?
Of course, yeah.
Again, it's picking up that point, guys, that low CO2 does not mean low energy costs. And the main reason why the SAP calculation there that you can see and the EPC rating that's coming out of it is at a C or a D is primarily driven by that energy cost basis, which is quite a key point within the EPC calculation. So here's a first little kind of red light or a warning sign that where on our employers' requirements documents or where we are requiring as part of planning or other guidance to achieve an EPC rating of A or B, as Emily's quite rightfully pointed out, the introduction then of more renewable technologies or the push towards a more passive envelope to the building, to passive house standards or improved standards, is really going to be a drive. And myself and Emily and Petrula, one of my other members of staff, have been doing some research on a whole range of different housing types and different technologies. And we are finding, unless we really concentrate on those passive building elements, that at the moment under the new SAP 10.1, which seems to be the one that's going to be driven with Part L with the building regulations, you're just coming in an EPC of C and sometimes just narrowly getting a B. So early stage development and early stage review, I would really strongly recommend at the planning stage and at the early concept stage, run some early stage SAP assessments, just so that it gives you a real clear indication of what that means. Primarily the cost driven element, not anything to do with lowering CO2, but just the cost element. Thanks, Emily.
That's okay, exactly. So here's the updated primary energy factors. Again, we've got the current methodology, SAP 2012, and the proposed methodology, SAP 10.1. And we can see that mains gas has reduced slightly. However, electricity has reduced quite significantly yet again, same as CO2, at 51%. So we're going from 3.07 kilowatt hour of energy put in to get a kilowatt hour of energy out to 1.5.01. However, here we can see that electricity is still higher than mains gas. So now that primary energy is going to be a main performance metric under the new Part L, we've just got to make sure that we achieve this primary energy target, especially if we do go down a direct electric heating system. As with the EPC, you might need building fabric improvements and renewable technologies and battery storage on site to achieve that primary energy target. So here's the Part L consultation key updates. So criterion 1 will focus on primary energy as well as CO2. So again, careful design is required with electric heating. Householder affordability, so there may be a new regulation that requires housing to be affordable with regards to running costs for heating, hot water and lighting. So these could be based on an EPC rating. And again, direct electric heating, as we saw on the previous slide, can be quite expensive if you don't make improvements elsewhere in order to reduce those energy demands, especially the space heating demand and hot water. Summer overheating, a new regulation, the government has been asked to put in place a new regulation that stops properties that are prone to overheating being constructed. So at the moment in London, we do see CPC TM59 dynamic simulations be carried out to make sure that developments comply with that criteria. Outside of London, you don't see it so much, but with this new regulation, you might see it a bit more, just to make sure that homes are tested to make sure that they don't have a summer overheating risk. Air pressure testing. So Part F was also released with the consultation, and it indicated that all dwellings will need to be air pressure tested. At the moment, that is quite common practice, but we do have the choice to test a sample of dwellings and add 2 to the average test result for the dwellings not being tested. But with the new Part F, it looks like that we will have to test all properties and we won't have that choice. Electricity CO2 emission factors, primary energy factors, and the electricity costs have all changed, as we saw on the previous slides. There are currently 2 options proposed for the notional dwelling specification, and that's used to calculate the target emission rate and your target primary energy rate. So option 1 looks at improved building fabric, and it's almost in line with the Passivhaus standards, so it's got enhanced side values for the thermal bridging and triple glazing, and that will provide an estimated 20% CO2 emission reduction over the current regulations. Option 2 looks at improvements through technologies rather than building fabric. So they're actually going to put PV into the target emission rate for option 2. And that will provide an estimated 31% CO2 emission reduction over the current building regulations. Option 2 is the government's preferred option. However, this does have the highest estimated increase in build costs, as you can see there, £4,800, but it does have the highest estimated savings to the householder as well. So this is probably why it's the preferred option by the government. It is expected that builders will choose less costly ways to meeting those targets. So this is the GLA Draft London Plan, which has been issued for the intent to publish. So policy SI2 does look at minimising greenhouse gas emissions and is similar to policy 5.2 of the current London Plan. And you still have the energy hierarchy: be lean, be clean, be green. So be lean is using less energy, by applying passive measures such as improving building fabric, mechanical ventilation for heat recovery, and efficient heating controls. Be clean, so that's looking at district heating networks, whether you're connecting to one or create one. And be green is your renewable technologies, so air source heat pumps, PV. There is a new step in this energy hierarchy, be seen, which looks at to monitor, verify and report on energy performance. Residential development should achieve a 10% reduction in CO2 emissions and over the be lean stage. So this is pushing on the fabric first approach. And the non-residential development should achieve a 15% reduction in CO2 emissions over the be lean stage. It's also worth noting that the carbon offset fund payment has increased to £95 per tonne of CO2 over 30 years, which is £2,850 per tonne of CO2. It's currently £60 per tonne of CO2, which is £1,800. So it's quite a big uplift in costs there. And this is just encouraging us to make all the improvements on the site before we pay into the carbon offset fund. Terry, do you want to talk about the new guidelines that have been released by the GLA for the B scene?
They are pushing and increasingly pushing now on having a whole range of parameters for that energy to be monitored. So therefore, what you put within your planning application and what you're declaring within your CO2 emissions that you're going to be able to achieve, that they will want to monitor over a year, 2 year, 3 year period. This is something we're already getting used to with the likes of Islington Council, where we're being asked increasingly now to monitor the levels of our CO2 against what we originally put in planning. However, and the big however is how someone measures that metric against the way residents use energy, or the way we're predicting an energy use over a weather condition. So I still think there'll be some work in that particular area, but it's one to be very much aware of, that when stipulating or stating CO2 reductions in the energy strategy, excuse me, my apologies, in doing that in the strategy, is being really aware that we will be called to task at the end of the job and in operation to show how closely we are operating within those parameters. Thanks, Emily.
Thank you, Terry. So here's a table showing a comparison between the two notional buildings that I explained in the previous slide, and also if we applied Passivhaus principles. So here we can see where the U values have been updated in blue. So for notional building 1, we can see the external wall U value has been improved from 0.18 watts per meter squared Kelvin to 0.15. And the roofs have gone from 0.13 to 0.11. This is the biggest one for the windows. So currently we have a U value of 1.4 in our notional building, which is a standard double glazing unit. However, notional building 1 does look at triple glazing with a U value of 0.8 and a G value, so solar transmittance value, of 0.57. And as I said, the thermal bridging, so they look at enhanced side values for the thermal bridging compared to accredited construction detail. So this is just emphasising that we should insulate around our cold bridging junctions to reduce heat loss through those areas. Notional building 2, the fabric hasn't been improved that much compared to notional building. We've just got a slight improvement on the roof and possibly high-end double glazing, maybe triple glazing for the windows of 1.2, but solar transmittance of 0.63. The thermal bridging has only been slightly improved over the current notional building, so not big improvements there, but the biggest change is this solar PV that they're adding to the notional building. So if we look at the Passivhaus principles, we can see that the U values for the external wall has been slightly improved, but not a significant amount, and the same with the floors and roof. We have triple glazing, which is probably the biggest step, and very enhanced thermal bridging, because the Passivhaus is considered thermal bridge free, and a very low air permeability rate. So we're looking at reducing the heat loss and also making the building very airtight. And due to that airtightness, a Passivhaus does require mechanical ventilation with heat recovery to ensure that we have enough sufficient airflow for our occupants to breathe. So the GLA require a 35% reduction in CO2, and then anything left over to zero carbon has to be paid off into a carbon offset fund. And we applied that notional building 2 specification to a sample SAP calculation and had to look to see how much PV would be required to achieve the 35% using the GLA CO2 emission factors. And here we can see that for individual gas boilers, we'd need 14 panels, for electric heating 8, and community heating with air source heat pump 6. And then for the carbon offset fund payment, we'd have to pay this much. And then for the total cost with PV panels, we can see here it ranges from about £11,500 to £23,000. But applying those Passivhaus measures and reducing that space heating demand, we can significantly reduce the number of PV panels required. So for gas boilers, 7 panels are required to the 35% reduction. For electric heating, we'd only need 1 panel And for community heating with air source heat pump, we wouldn't need any to achieve that 35% improvement over the target emission rate. So this, even though the carbon offset fund payment is very similar because we're achieving 35% in both of the options, total cost is reduced because we don't have to spend so much on the solar PV panels. And then if we look at the running costs, we can see here that the main issue is electric heating. So we've got £928 estimated running costs for space heating and hot water. And even with the passive house applied, we still got £626. And that's because of your hot water demand, which is still quite large. And when we compare that to individual gas boilers or the community heating with air source heat pump, it's a lot extra. And this can lead to your poor EPC rating. So even with the improvements, we still encourage the use of renewable technologies to ensure that we reduce that running cost for your hot water. So what's the estimated construction cost for Passive House? So this is the Passive House certification. The Passive House Trust carried out a study in October 2019, and that indicated that you'd have an uplift cost of approximately 8 to 11% higher compared to a standard development, typical building regulations development. And that's by applying best practice extra costs, a simple design. And the extra cost is estimated to be reduced, uplift cost, is it estimated to be reduced to 4% if the quality assurance process of Passive House does become a standard or is adopted nationwide. The areas that are shown to have the greatest additional costs is wall and roof structures, and that's due to the additional insulation and the additional detailing for the thermal regime and the air tightness. Use of MVHR. So if you went for Passive House certification, we would encourage that a Passive House Institute certified MVHR unit is used, because otherwise you have to apply a penalty of 12% to the efficiency of that MVHR unit. This does have an uplift in costs. As you can see, a non-PHI unit is about £1,000, and then a typical PHI certified unit is about £2,800. But this is purely because there's limited competition on the market. So if it is adopted nationwide or becomes a standard, it's likely that the competition will become less and the cost will be reduced.
Emily, just one point to make on the two MVHRs there, guys, is is the MVHR certificated by Passive House Institute is a much larger unit, dealing with much larger quantities of air, because obviously they're looking at the MVHR within a passive house having to deal with much higher ventilation rates due to the high levels of air tightness, whereas the non-Passive House Institute MVHR unit is more along the lines of the ones we're currently using within homes. So two areas there. One is obviously the larger air quantities to move, and the second one is the certified MVHR unit is getting on for almost double the size. So if we are going down that particular route, and that would be something that you'd look at from a passive house condition, early stage modelling with the architects and the layout of the dwelling are really important. That whole idea of adopting passive house, if that would be a route that would be chosen, needs to be taken on really from the most earliest stages of the scheme. It's the reason why there's a balance between the statement of passive house principles, so doing something that then brings our passive conditions down as much as possible, over actually going for certification, because obviously where we're moving to certification, certain equipment has to be used, and as a consequence then that has a size and design implication to it. So balance both of those when we're looking, because they will have implications obviously on the cost of the scheme. Thanks, Emily.
That's okay. So the air tightness testing, that's also shown to have a bigger additional cost, and that's just due to the more rigorous standards. And also we recommend that you air pressure test multiple times during the construction. So when the air tightness layer is put in, you air pressure test it to make sure you're achieving your target. And then when you have surfaces penetrating the air tightness layer, test it again just to make sure that the air tightness layer hasn't been damaged and you're still achieving your target. And then the final air pressure test as well.
We could almost be doing this on a first fix, second fix basis. So an air pressure test at the end of the first fix stage, and then a second air pressure test at the end of the second fix may be a way of accommodating that kind of air tightness testing.
Exactly. And also site supervision is shown to have an uplift cost. However, that can be reduced by applying best practice across the site. I'll now pass you over to Terry, who's going to talk about the heat pumps.
Hi everyone. Right, I'm gonna look at 4 areas for heat pumps today, and we've primarily chosen air source heat pumps, but as you know, or air source and water source. Our second system there looks at both an air source and a water source system. We haven't selected ground source, but ground source is obviously another option, and part of our ongoing seminars is that we will do a few seminars specifically on air source, on all heat pump arrangements. But today, just as a little analysis for you, as obviously air source heat pumps being the more cost-effective option, we just wanted to show you what those models were like. So I'm going to do 4 today. One is a centralised air source heat pump, which is a heat pump only. So it would be a system where we would be doing communal heating, but we would only be putting in air source heat pumps. The second one would be the same. It would be similar. It would be a communal air source heat pump arrangement, but in this case it would be an ambient heat network where within each of the dwellings we would be using a water source heat pump. So air source heat pump at a lower temperature, water source heat pump within the dwelling. The third one I'm going to look at is an individual air source system with an external compressor, something you'll probably be much more used to in seeing in air conditioning environments. And then the last one I'm going to go to is on a hybrid system. We're looking at a heat network that uses both gas boilers and air source heat pumps, but using the 2 technologies where they are most beneficial. So moving on. Just jumped. On the first system, this is an air source only system, and as you can see over onto the left, we have a number of compressor units, and these units would be mounted either up on the roof of a development, or they would be down within the landscaping within a containment area. It's very, very similar to a district heating system at the moment. There would be a thermal store and a thermal store arrangement, and then what we're showing is a flow temperature and a return temperature back to the system. Over onto the right, where you see my cursor moving, we've done some analysis on coefficients of performance, and the reasons we've chosen COP of 3 and a COP of 2.5 is the coefficient of performance, and just reiterating what that means. So for every 1 kilowatt of energy generated electricity, the COP of 2.5 will mean I get 2.5 kilowatts worth of heat out, and on the COP of 3, for every 1 kilowatt of electrical energy produced, I'll be getting 3 kilowatts worth of heat out. The reason we've chosen 2.5 is obviously that's the main key area if you are going for renewable heat incentive. So if you are getting funding for your air source heat pump to lower the overall costs, the air source heat pump system must run at an efficiency of at least a COP of 2.5. However, here I want to show you and you can see in the way that the system is operated that an air source heat pump system runs at a lower temperature. Primarily, that heat pump system is probably only wanting to run to 50, 55 degrees C. And where these are most prevalently used within the commercial environment, they will be used for heating only. So supplying air heating into an office accommodation where the hot water will be made up of either a calorifier, electrical central heating system, or point of use heaters within the toilets and shower areas. However, and this is the big however, where we're using this type of technology within the domestic environment, our air source heat pumps have not only got to do the heating, they've also got to do the hot water. So where we would be saying and looking at the maximum flow temperatures coming out of our system at 55 would absolutely be perfect for an underfloor heating system. So if we're running our underfloor heating system at 35, maybe 38 degrees, maybe even pushing it as high as 40 degrees C, the air source heat pump is well able to act within those areas. However, where I then need to have that hot water pushed up to 60 degrees C for part of my Legionella treatment, this is where the heat pump then starts to, within a domestic environment, struggle a little bit more. And then if I bring your attention to my little graph over on the right hand side, if you follow up where we're looking at a temperature in the winter time of between 0 and 5 degrees, often what a UK temperature, an average UK temperature is during the summertime, you will see that we're just about getting in at our 45 to 55 degree temperature for our COP to make sure that we achieve that condition during the winter time. Obviously during the summer, and if it ever happens in England that we get somewhere above 25 degrees C and it gets to 30 and I've got my shorts on and the legs are out, which you wouldn't want to see, but there you go. You wouldn't want to see my legs, but the COP gets better. But so when we look down there at 25 to 30 degrees C, we can see our air source heat pump then is more than adequate to actually push a condition of maybe 60 or 65 degrees C. So the particular thing to this part of technology, and wanting to express that we're pretty agnostic on that technology, but what we wanted to point out is the pros and cons of using the particular technology. If it's an air source only system, that running at the lower temperatures could mean that when you get to your HIU, your heat interface unit, the little boiler unit that is within each dwelling that then delivers the hot water, if I'm passing that round at 55 degrees C, I need to achieve 50 degrees C at the sink tap after 1 minute to comply with building regulations. And in doing that, the plate or the mechanism that's within the HIU, the heat interface unit, has about a 3 or 4 degree drop. So if I'm supplying in on my primary side, my main distribution into the HIU at 55, I can only drop 3 or 4 degrees to then ensure that I'm getting 50 degrees C at the tap in 1 minute for my dwelling. So as you can see, if you're designing in this way, you've got to be really, really detailed about how that temperature is supplied and how it's delivered to each individual dwelling. And if there are value engineering exercises going on throughout the scheme, if there are other changes within like the distribution, it's key that it comes back to the design of the flow and return temperatures all the time, because if I drop that temperature too much and I can't achieve the 50 degrees C at the tap after 1 minute, I've already fallen foul of my building regulations. And if the only option then is, and I can turn up the temperature of the air source heat pump, so I can make the air source heat pump work harder. However, if you follow my graph up, the harder I make my air source heat pump work, the worse the COP gets, because the more energy I use to generate that same amount of heat. So I could be moving towards a COP that, one, would take us outside of your renewable heat incentive, so may mean that you can't claim that funding, or two, it may mean that you're using much more energy. Now, if you remember back to when we were talking earlier, the most important, or one of the most important, or two important points for me is that I want the system to be as low CO2 as possible. We have to do that as part of planning, and we're having to, in an environmental age, of driving that CO2 down as much as possible. However, and the big however is I must make the energy affordable for the residents that are using it at the end of the scheme. It's no good me providing a zero carbon site that no one can afford to use. So that instance of raising the temperature in an air source only system, be careful. An air source only system needs to work at lower temperatures to be as energy efficient as possible. So it's just a warning sign there. Another couple of little bits and pieces of design consideration is obviously an air source heat pump has a fan, so the noise, and especially if these are out on a roof on a development, the low frequency noise, so the fan switching on and off early in the morning or late in the evening when the ambient noise in the vicinity is much lower, means that you have a perception of that low frequency noise, which often can cause issues. So noise evaluations on air source heat pumps, especially where they are near dwellings, is a really big one. The visual impact, these units are about 1.7 high there, as you can see, about 2 meters long and about 800 meters wide. So they do make quite an impact either on the roof area or within a ground floor plant location, and a cost element. Each one of those units is around about 23k each for about 43 kilowatts thermal load. So it's one just to be aware of. So noise, visual, weight, they're about half a ton each. If you're going air source only, really, I know on all designs you should really break down, but on this one, really work on those distribution temperatures. It's really important.
Terry, can I just very briefly interrupt you? I understand that Bernice is having a problem seeing some of the slides. I know some other people have come back and said that they're okay. I just want to check that everybody else is all right and no one else is having any difficulties.
Okay, Sarah, shall I continue?
Yes, please. Thank you. Sorry.
Yeah, okay. And Bernice and anyone else that's listening, we will be the full set of slides that we've got here. Plus, we've got some really good working notes that both Emily and Petrula have put together. We will be sending out to everyone. So if there is any difficulty, we will send these out. And also, if there is any difficulty, just come back to me or Emily on a Teams discussion, and we're more than happy to talk through what's there. Much more than happy to talk through what's there. So if there is any difficulty, guys, just come straight back to me, drop a note, we'll send the slides through. If you need any further information, just call and we'll go through it with you. So I hope you don't have difficulty for the rest of the presentation. On this second one, this is kind of like a hybrid arrangement of an air source system. So it's then over in the corner here, you'll notice straight away that there are less air source heat pumps, because in this particular instance, you'll notice that the distribution temperatures have been lowered considerably. So what this is attempting to do is it's accepting the fact that the air source heat pump needs to work at lower temperatures. It's then saying, well, we'll distribute at that lower temperature, so down to 25 or 30 degrees C. But when you get within the dwelling, if you can see where my cursor is going round, there then is a further water source heat pump. So air is supplied to that water source heat pump that then produces the heat up to 60 degrees C. Now, these water source heat pumps are not like the heat interface units that you're used to that can then both do hot water and heating instantaneously generated from the unit. You will then further need a hot water storage vessel where the water source heat pump will store that water to then be able to be distributed out within the dwelling. So therefore, within this kind of ambient air system, we are lowering the temperature as we're distributing. We're then coming into a second unit, which is a water source heat pump within the dwelling, and then we have a hot water storage tank that then distributes out to the radiators, the baths, showers and taps. That hot water storage facility also has a immersion heater in it. Now, the pros, the good points of this one, and a lot of people will be aware of overheating in communal spaces with distribution systems being installed in airtight buildings, is we are distributing at a much lower temperature. However, as a consequence of that, I am having to use a second technology and a storage facility to then communicate that energy to the dwelling. So it means you're almost doubling up on that technology. From a maintenance point of view, you then have the maintenance of the air source heat pumps and the maintenance of a water source heat pump and a heating storage facility. But it allows you to use the benefits of both of those technologies. Downsides is obviously cost of the installation. Downside is the maintenance criteria that is required, and the additional space for the hot water storage facility that's taking up otherwise very useful storage within the dwelling. However, it is a way of dealing with a heat pump arrangement only. So where there is a development where for whatever reason you only want a heat pump only, this will give you the opportunity to do that. It still has all of the implications of weight and noise because we are using the air source heat pumps again up on the roof, so you will have that. The other point to be aware of is that the pipework in this kind of design will be larger because we're having to distribute a larger amount of water for the water source heat pump to use that temperature to then generate the requirements within the dwelling. So pipework sizes are still large to generate the kinds of water distribution that we need. Moving on to the individual system, and this may be one that you've seen in the past anyway. Look at my cursor moving around on the balcony of the 3D image there, down on the side of the building and on the side of the building, as you can see in the elevation image. Here you would have a compressor, an individual compressor for each individual dwelling, and it would be normally within a small block. Again, this would be where you would be driving towards an air source only system, and you would have the heat pump within the dwelling with a hot water storage facility within the heat pump as a whole, and then, as I say, the compressor out on the wall alongside. One of the areas for this particular one is that the compressor needs to be within a 30-metre distance as a maximum for the heat pump. So therefore, you have limitations on the placing of that compressor and where you're going to put it in relation to the dwelling. The other one is it still has the same issues of a fan, as you can see, so low frequency noise and generation, especially where, as you can see on this one, it's very close to an adjoining property, may have an issue. An interesting point that I wanted to raise for you, that if you were thinking about these and you didn't want to go down the additional cost of underfloor heating, if you look at the radiator sizing to the size there, when we normally size a radiator at 70 degrees flow, the radiator is around about a width of about 300 millimetres. if I drop that flow temperature to around about 50 degrees C, where the heat pump is really good and is really very, very efficient, that radiator almost grows by 2.5 times. So do be aware where you are using heat pumps in a situation where you're not using underfloor heating. The lower flow temperature within the dwelling means that the radiators do go up in size. So do be aware of that aesthetic implication to the dwelling, that a much larger radiator. I'm going to move on to the last one now, which is a hybrid system. So here you will see that we still have the gas boilers, and we have the gas boilers as we're very used to in a communal heating system. And then you'll notice down here I've put air source heat pumps in where you would normally have a CHP, a combined heat and power unit. So all I'm doing in this kind of situation is taking out the CHP and taking out the load of the CHP and putting in an air source heat pump. Now the idea here is, and as you can see in the temperatures, because I've got my boiler working to a thermal store and I've got a nice mixing valve arrangement here, I can allow my gas boilers to work at the temperature that they most feel happy at, which is around 70 to 80 degrees C. I can also allow my heat pump system to work at its system, its temperature, where it feels happy. So during the winter time, I can allow that temperature, and as we see over on our graph here, I can allow that temperature of the heat pump to go right down to 40 or 45 degrees C, and then even at 5, at 0, between 0 and 5 degrees C, I can allow my heat pump to work much lower, deliver me a really good COP, and then use it as a preheat into my system. So therefore, as opposed to just bringing over my water at whatever I'm getting it in at the mains of 10 or 12 or 8 degrees C, I can use the air source heat pumps to preheat that water up to 40 degrees C, and then reduce the size of my boilers just to pick up that heat from 40 degrees C, then up to the 70 degrees C, that then I can circulate. That means my HIUs, my heat interface units, are at a much happier temperature to deliver the 50 degrees within the dwelling. And do remember here, 70 is a maximum. I can reduce that temperature right down to the 55 degrees C that we look with the air source heat pump. But if we have issues, I've got no problems in lifting my temperature to 60 degrees C, 65 degrees C, where we feel is the best area to operate. The second point is, and the really, really good point that I like about this kind of system, is during the summer months, when I'm getting this air source heat pump to run at probably a COP of 4.5, maybe even 5, you know, let's go into the realms of Alice in Wonderland, you know, but let's say at least we get it to a COP of 4 or maybe a little higher. I could be delivering the whole system with air source heat pumps. I could be delivering that technology with, because I'm running it at a COP of at least 1 to 4, at the same price as gas. So therefore, we won't see a difference in cost to the resident. And then as soon as I get to the winter time period, where that air source heat pump is then struggling, I use my gas. I use my gas to then back that up. So it means that I'm able to say to a resident throughout the year that the temperature of their heat, the cost of their heating and hot water, whether it's supplied by the air source heat pump, which is the lower CO2, or whether it's supplied by a balance of the two, so therefore the gas boiler and the air source heat pump with a makeup, I will be able to show the best opportunity for reducing their costs and their use of that energy. We have trialled this 3 or 4 times now on pre-applications and planning applications with the GLA. And the GLA have really liked it, and they've liked it for two reasons. One, we can show the reductions in CO2 that are required, and reductions that are in excess of their 35%. And as Emily has made the point earlier on, the more reductions I can get on site, the more we take away from the contribution to be made as part of the Section 106 payment for the CO2 level. So I can reduce that. But what they've also liked is, as part of our energy strategies, we have really majored on how much is that cost for a resident. What does it actually mean to a resident when I'm saving that CO2? And what does it mean as the EPC, and what does the EPC look like? So where I feel comfortable as an engineer, I'm using the right technology at the right time. So summertime use, wintertime use with backup. So here I think the hybrid has got a lot to offer in the long-term market. It also still puts us within the environment that I'm only using a small amount of air source heat pump, so the location of those is easier to manage, as well as weight, noise, and other issues. And where we've been used to communal heating, whether we like it or not for whatever reason, where we've been used to that parameter, this with our maintenance contractors and the way that we're used to dealing with it is still within the realms of a comfortable level for a maintenance contractor to operate. Just as a final couple of recommendations, obviously we, through all of what we've talked about, and Emily with the building regulations and the Passivhaus review earlier, and with my discussions on the air source heat pump, we really recommend get that sustainability consultant in at an early stage so that you can start looking at some of these strategies. And here we can definitely help early on in the day to show you what the implications are on fabric size, on room sizes, on dwelling size of the different kinds of technologies, so that you can make the right financial decisions on the amount of units and the size of those units. Fabric first approach, and as you know, we've always pushed that, but it's a part we will be pushing more and more in the future, and we think it'll have a greater part to play. Myself and Emily and Petrula and Dr. Chris Marion, one of our other guys, is also pushing together on putting a research paper that we'll be able to show you, where we've been analysing this on 7 or 8 different housing types, as well as off-site construction. We've been working with an off-site construction company called Tallow House, where we've been working with them to see what we can do with the fabric first conditions. Major, and I know we've said it all the way through this presentation, consider the end user, consider that cost, consider what it will actually mean for someone in making sure that they can pay their bills, and they can pay their bills effectively. I think if one message goes out from today is low CO2 does not mean low energy costs by any stretch of the imagination, and the balance of that and the working of a team to deliver that is a really important thing. Investigate different approaches. If anyone tells you there's one silver bullet, run a mile. I think it's always been my way. Each technology has an area to work. An air source only system may work where it's off gas. So there may be opportunities to look at that air source heat pump system, or a ground source heat pump system where you are off of gas connection. There are still lots of things to play. There may be philosophical reasons why you will only want to go down a one technology system. There may very well be, as part and parcel of what you're trying to achieve. But all we're saying is when you are taking those decisions, take them with your eyes wide open, so that you know the implications of what could come out of that if there are changes during the construction process, which there often is. Again, as we've said, we've had recent successes in the planning stages with GLA under the draft London plan, because obviously it still is at the moment, but we've had some really good warm feelings over the kinds of things that we're trying to do, where we're saying not only low CO2, really important, and we all want to do it, and I watch as many David Attenborough programs as everyone else does. So I want to save that CO2, but also it must be affordable. It must be affordable to people. I think that's a big drive. So that one we really want to look at, and then looking at strategies so that we get the best out of them. And one thing, just to let you know, just as we conclude here, we are also keeping our ear to the ground on hydrogen ready boilers. Worcester Bosch have already put out a boiler which is hydrogen ready. So where we're thinking in the not too distant future of mixing the gas network with both hydrogen and normal gas, they have already produced a gas boiler in January, which they are pushing forward as hydrogen ready. So what we're doing is we're very much keeping our ear to the ground on that one and listening and watching what goes on. And it was very, very interesting that the Minister for the Department of Energy was at the opening of that new boiler. So I think there is government interest as well, especially when we look to this 2025 banning on gas boilers. There may be some leverage where it's a gas boiler that is hydrogen ready. So we will keep our ear to the ground on that, and we'll let you know more about that. So therefore, thank you for your time, and if you've got any questions.